Hello friend, welcome to the electrical neuron. Today we have to discuss a new chapter on inductance, that is self and mutual inductance. So previously we have discussed the inductance of single phase two-wire line. So today we have to discuss the self and mutual inductance. Okay, so let's get started our new topic. Okay friend, so here the inductance per phase for the single phase two airline shown in this figure. Here there is a inductance of two airline, that is VR1 and that is VR2, and there are two line and current flowing, one is I2, another current I2 dash, and there are inductance of L double one is the self inductance of inductance 1, and L double 2 is the inductance of self inductance of inductance 2, and there is M12 inductance between first conductor which linked to the second conductor, and M21 inductance between two conductor that is linked second conductor with the first conductor, and thus are equal in each other. So thus can also be expressed in terms of self inductance of each inductor and their mutual inductance. Those are the L11, L22 are the self inductance, and M12, M21 are the mutual inductance. So here figure in the single phase two-wire line viewed as two magnetically coupled coil, and they are coupled with magnetically, not electrically. Okay, so let the consider the single phase circuit represented by the two coil characterized by the self inductance and mutual inductance, whatever I have already seen in this figure. So the single phase line view as two magnetically coupled coil, and the magnetically polarity is known by dot symbol. There's a two dot symbol, and those are coupled by the sum of these two dot. Okay, and the flux linkage, those are lambda 1 and lambda 2, those are two flux. One is lambda 1 flux, another one is lambda 2 flux, and those are the flux linkage. Here can be written as lambda 1 is equal to L11 I1 plus M12 I2, and lambda 2 is equal to flux linkage by inductor 2, that is equal to M21 I1 plus L21 I2. That is our self inductance flux, and that is our mutual inductance flux, and that is our mutual inductance flux of the inductor 2, and that is our inductor 2 self inductance flux linkage. Okay, let me erase. Going to our next slide. So since we get, what do we get? The I2 is equal to minus of I1. So let me correct one thing. If this one is this is not I2, this one is our I1. Okay, so here I2 is equal to minus of I1, or I1 is equal to minus of I2 simultaneously. This, so by putting this I2 is equal to minus 1 in this equation, I2 is equal to minus 1. That means what happened? Lambda 1 is equal to L11 I1 plus minus of I1 into M12. So here by taking I1 as a common, then L11 minus of M12 will be common to what closed circuit from this equation. Okay, and by by putting I1 is equal to minus of I2 in the second equation, and by comparing this like this, we will get lambda 1 is equal to L11 minus M12 I1, and lambda 2 is equal to minus of M21 plus L22 I2, and therefore we can write L1, that is inductance of inductor 1, that is equal to L11 minus M12. This is our L1, and L2, that is our that is our inductance of inductor 2, that is minus of M21 plus L22, that is here. Okay, and we have already know in the previous lecture, that is L inductance is equal to flux linkage phi, or it can be represented as a lambda divided by I. From this only this equation will become. So comparing equation 40 and 41 with equation 33 and 34, we'll get L11 is equal to L22 is equal to 0.4605 log 1 divided by R dash. In the previous lecture we have studied all the thing. It is millihenry per kilometer unit, and M12 are equal to M21. This mutual inductance are equal, so that is equal to 0.4605 log 1 upon D. So this equation we have already studied. From this equation only we will get that self inductance and mutual inductance. So L1 is equal to, in this equation number 40, L1 is equal to L11 minus M12, and by putting this, L11 is equal to 0.4605 log 1 divided by R dash, and M12 is equal to 0.465 log 1 divided by D. So we will get the L1 and L2 simultaneously. So here, on the above described approach of self and mutual inductance can be extended to a group of conductor. So let us consider a conductor carrying a phase current like I1, I2 and IN, and such that by adding all those equations, that means I1 plus I2 plus ... 2 plus IN is equal to 0. This is our generalized formula for the flux linkage of current I, and is given by, let here, flux linkage lambda 1 is equal to L11 I1 plus summation of j is equal to 1 to n m ij and ij. This is our generalized formula.